So let's look at this problem where we have a non-stationary process and I want to do something to it to induce the stationarity. So generally if you pass a process through a system, if it is non-stationary, generally it will turn out to be non-stationary. But in some special cases, you can induce some well-behaved nature. So essentially, so if you look at, so I want to look through this example. Let's say Wiener process, it is non-stationary, and it's Gaussian. So it's in fact a zero mean Gaussian to start with, a Gaussian process with an autocorrelation function RWT1 T2, which is of the form alpha minimum of T1 comma T2. So this is our starting point. I'm going to phase modulate. So in other words, I'm going to look at the output to be of this form. Alright, so let me explain to you what all this. So as if this is a carrier in electrical engineering. So it's this is phase modulation. The input waveform is phase modulated because it is sitting in the phase of a carrier at a central frequency omega naught. And when it, by the time it comes to the other side, we are assuming that there is also a random phase theta. So you can think of this as the received waveform. And so I'm going to look at analyze the characteristics of this stochastic process x of t. Quickly you can see that its mean is 0, and I'm going to assume that these two are independent. In other words, the Wiener process is independent of the random phase, and the phase is of course uniform. So expected value of x of t, as you can see from here, expected value of cos omega naught t plus x of t. Let me expand this as, so it's going to be this multiplied by cos theta, but because theta and x of t are independent, and then this is expected value of sine omega naught t plus x of t, not x of t, w of t here, and expected value of sine theta. But expected value of cos theta and sin theta both are 0. This you can see quickly because this is simply integral 0 to 2 pi 1 over 2 pi cos 2 pi or sin 2 cos theta d theta. That of course is integral is sin theta over 2 pi 0 to 2 pi, and that's 0. So same thing here also, both are 0. Same argument you replace by sin. So the mean value is of course 0, and now comes the interesting part of the autocorrelation function. So Rxx t1 comma t2 is going to be expected value of cosine omega naught t1 plus w of t1 plus theta multiplied by cosine of omega naught t2 plus w of t2 plus theta. So if you use the expression cos A cos B is half of cosine A plus B plus cosine A minus B, you get expected value of cos of A plus B. So that's going to be the sum of all this. So that's omega naught T1 plus T2 plus WT1 plus WT2 plus 2 theta and the cosine closes here plus another expression involving cosine again, because expected value of cosine of omega W naught or omega naught T1 minus T2 plus W T1 minus W T2. That's it. Because this is A, this is B. So A plus B is, I have written here. A minus B, notice that the theta goes away. A minus B, you get that one. And so very quickly, if you, let's take each term, but so remember this is a plus, so expected value of this, again you go through the same procedure, you can show it to be 0 because of this 2 theta. If you expand this, this is going to be cosine of this multiplied by cos 2 theta, multiplied by expected value of cos 2 theta, which is 0, minus sine of this multiplied by expected value of sine 2 theta, which is 0. So I'll rewrite here. So the interesting thing is this will turn out to be Rxx t1 comma t2 turns out to be now expected value of, so let me call t1 minus t2 to be tau. So this is cos omega naught tau plus some z, where z is of course, so there is a half here, and I'm going to call this to be z. So notice that what I'm defining z is wt1 minus wt2, and you can quickly see expected value of z itself is 0, and z is Gaussian with the 0 mean now, so its variance is going to be from here expected value of wt1 minus wt2 the whole squared. So this of course if you expand you get expected value of wt1 squared plus expected value of w squared t2 minus 2 expected value of wt1 wt2. So this is, you put t1 equal to t2 there, so this is simply alpha t1. Here it is plus alpha t2 because t1 equal to t2. Notice that this is rww t1 comma t1, right? And this is rww t1 comma t2. So this is minus 2 minimum of alpha comma t1 comma t2, so this is 2 t1 if t1 is less than t2. So this will turn out to be, you can see t1 minus t2 minus t1, but t2 is greater than, so this I can write it as t2 minus t1 if t2 is greater if t1 is less than t2, which is t2 is greater than t1. So this is positive. And if it is the other way, it will turn out to be t1 minus t2. So this is, you can see, you can put an absolute value sign and then you don't have to do this. So this will turn out, sigma squared turns out to be tau itself. But so the question is, how do you evaluate this? So if you keep expanding this is, first of all, this concludes that the output is Whiteson stationary because, so I can write at this point Rxx tau is, if I expand that half cos omega naught tau, then expected value of cos z minus sine omega naught tau, expected value of sine z. So there is a half here, but notice that where z is a normal random variable with a zero mean random variable with variance alpha tau. So now there is, so the question is, how do you express this? So on the other hand, if you look at the characteristic function of z, that's now expected value of e raised to j omega z. This is for a zero mean random variable, it is omega squared z squared by 2. So if you put omega equal to 1, this leads us that expected value of cos z plus j expected value of sine z is equal to e raised to minus simply sigma z squared by 2. So notice that that gives you expected value of cos z is the real part, which is e raised to minus z squared by 2, and expected value of sine z is 0. So this term actually goes to 0, and this we have the answer, so I'll just copy it here. Rxx tau would turn out to be half cosine omega naught tau multiplied by e raised to minus the variance. Variance happens to be alpha by 2 tau. So notice that the output process is, so this implies that x of t is White's and stationary. So what we have been able to manage is through phase modulation, we have the output process x of t has more structure in other words, in terms of stationarity compared to the input process. So here is an example where through a nonlinear instantaneous memoryless transformation, a process which is a process has been made to have more structure or more well behaved because the non-stationarity at the input has been transformed to stationarity. So if you want, you can also find the power spectrum by taking the Fourier transform. So the power spectrum of this is going to be essentially 1 over alpha squared plus omega squared. And so this is of the form alpha squared plus omega squared. But because of the omega, so it will be a shifted version here. Maybe a constant here. So essentially the power spectrum will look like with two bumps. This will be the power spectrum of the output process. And this is actually quadratic, so it's a low variation. So to summarize, this process is non-stationary, whereas this is now, we have shown it to be Whiteson stationary, so very well behavior, and its autocorrelation function is cosine omega naught tau e raised to minus alpha absolute value of tau. And the power spectrum is essentially a band pass shape at omega equal to omega naught.